Okay, lesson 3.2, maximums and minimums on an interval and extreme. Okay, and we're talking about extremes because I will enlighten you. Imagine a function that looks something like this. Okay, technically this could be considered a maximum, especially if you're talking about like a stock market or something. This is where it peaked and a trough. And then this is a peak and a trough also. Both maximums and minimums in terms of the terms. But the extremes are these two. The very highest point and the very lowest point. Which is exactly what we're trying to find. Okay? So that's why we've talked about this being a max and this being a min. This is the absolute highest point here. Absolute lowest point. And now, also we said within an interval, because technically if this were to go up forever and this go down forever, we wouldn't have an extreme max or min. In fact, we wouldn't have a max or min. It would go on forever and ever. We'd only have to talk about smaller maximums or turning points. So we're talking about an interval means this has a starting point and an ending point. So all the ones we're referring to start and end. So you have to have parameters for starting and ending. This parameter here, we start down here, end here. Well, our minimums actually are starting point. And in this one, our maximums are peak. This is important because when we go to derive the function, our derivatives, see these two would both be where velocity or tangents would be 0. They're not technically always the max and the min. The starting point or ending point could also be a max and min. And in our third example, that's exactly the case. The min and max are actually the starting and ending points, and the intervals when the tangents are horizontal are not extreme max or minimums. So what that means, when going through this theoretically, we got to find the derivatives and the starting and ending points and compare all four of those in order to find a max and a minimum. So let's go to our first example. Okay, first example says, find the extreme values of this function. Oh, nuts, I don't want red. Is equal to negative 2x cubed plus 9x squared plus 4. Okay. On the interval, very important, x is every real number between negative 1 and 5. So those are our intervals, but we also need to figure out where the max and minimums are, or, sorry, our horizontal tangents. To find a horizontal tangent, what do we have to do to this equation? Derive it. We have to derive the function. So we need to find f prime x. And when we go to derive this, 3 comes down, we get negative 6x squared plus 18x. This is our derivative function. With our derivative function, our tangent turning points, when they're horizontal, are when the slopes are equal to what? Anyone know? 0. There it is. Good. So the slope has to be 0. So in other words, what we're doing is we're going to set this equation equal to 0 and find out at what points of x our tangents, or the slopes of our tangents, are horizontal. So we set it equal to 0, we then go and factor. Well, I can factor out negative 6x, which is going to give me x minus 3 as another. So when we split these, our options are x at 0 and x when it equals 3. Well, these both exist in our interval because our interval is negative 1 to 5. Well, 0 and 3 both fall in between there. Okay, so those are turning points for sure. We don't know if they're maximums or minimums. And we also have the beginning and ending turning points. Not turning points, but beginning and ending points. So we got to take the original equation, f at x, and we got to solve for when x is equal to the starting point, negative 1. The ending point, which is 5. I'm going to put some space in there because I want to be in order. One of the turning points, which is 0, and the other turning point, which is 3. So we got to solve f at x, the original equation for all these points, and essentially find out what's the max, what's the min, which will be the highest point, which will be the lowest point. Well, guess what? We can do it. We're geniuses. So f at negative 1 gives us this equation, negative 2, negative 1 cubed, plus 9, negative 1 squared, plus 4. That gives us negative 1 times 2 is 2, minus 9 plus 4 gives us 6 minus 3. think that's wrong. They got something else. Oh. Negative 1 squared is positive 1. I'm so quick. 15. Okay. Maybe this is a maximum. Let's find out. Our next point along this was f at 0, which is going to give us negative 2, 0 cubed, plus 9, 0 squared, plus 4. Well, that's just going to be 4. All right, so we know that's not a maximum. Maybe it's a minimum. F at 3 was another coordinate. Negative 2, 3 cubed, plus 9, 3 squared, plus 4. 3 cubed is 27 times negative 2 is negative 54. 3 squared is 9 times 9 is 81 plus 4. That's going to give us 21, 7, 31. Yep. I should just look at the book. And f at 5 gives us negative 2, 5 cubed, plus 9, 5 squared, plus 4. Oh, geez. 125, double negative 250. 25 times 9, 225, plus 4. That gives us negative 25 plus 4, negative 21. So, let's try to compare all of our values here. There we go, we can see them. So our lowest point is negative 21, and our highest point is 31. So our max occurs when x is equal to 3. So that's one of the turning points that we found. And our minimum is actually our ending point when x is equal to 5. Right? So we probably have something shaped like this. We start, we go down, we come up, and then we go down. Where this is our maximum and this is our minimum. But maybe something like that in terms of a curve, if we're going to make sense of it. Okay? So that's example 1, finding max and min.